everybody. This is lecture 18 in the middle of the spring 2020 semester for my numerical methods class at Bethel University. It is after spring break and we are dealing with moving everything online because of the coronavirus. Another class that I'm teaching online is called Applied Statistics, which is really advanced undergraduate statistics. These two classes, numerical methods and applied statistics, are actually going to overlap a fair amount here in these next weeks because essentially we're trying to do data modeling. In lecture 18 here for numerical methods, we're doing Lagrange Interpolation. For my students, it's a review, but I think it's definitely a worthwhile review, and I hope all my students definitely pay attention well for this entire lecture. I will really try to emphasize the key points that we talked about before spring break. With Lagrange Interpolation, we're trying to match data points exactly. Okay, we're trying to estimate a function by matching it exactly at certain data points. With the other class, Applied Statistics, we're trying to estimate data points approximately, looking more for the trend rather than going through points exactly. By the way, at the end of the video, because of the coronavirus especially, I want to give you some encouragement. Bethel University is a Christian school, and I want to read from the Bible to give my students and anybody else who's interested some encouragement in these tough times. So here's the lecture plan. Plan for lecture 18. Again, the main topic is Lagrange Interpolation. So we are talking first about a simple example in the context of some key ideas. There's two key ideas that make Lagrange Interpolation work. They're the key ideas that Lagrange thought of first. We'll implement that for a nice example. There's something called an error theorem that gives you a bound for the error in the approximation under certain conditions. And the theorem, while still true for the simple example, is not really useful because we're not going to know what the underlying function is that we're trying to approximate. Secondly, we'll look at more Lagrange interpolation in the context of a second example. This will be a relatively simple function, the sine function that we're used to, though that is a transcendental function instead of an algebraic function, which does, in a sense, make it more complicated. And because of that fact, it ends up being messy numbers, okay? We need some technology. Now, Lagrange didn't have the technology that we have. He lived like 250 years ago or so. So he had to do everything by hand. We do have the luxury of still using some technology here, and that will be helpful. We'll use Mathematica here. The error theorem, it turns out, is more useful for the second example than for the first example. We'll be able to come up with a pretty nice error bound for the approximation. Sometimes, however, the error-bound theorem is not as good as it might be otherwise, you might say, because we're going to be able to look at some graphs and come up with even better estimates for the error based on those graphs. But of course, then we have to have the technology to make the graphs. Finally, at the end of the lecture, I'm going to give some words of warning. First of all, extrapolation can lead to larger errors. When you're going outside the data points, either to the right or to the left, you are in danger of being more off from the underlying function than you would be if you're doing interpolation. A second word of warning, especially when you got a lot of wild or random data, is to overfit the data. You got 100 data points, you could fit it with like a 99-degree polynomial, but that would be kind of nasty for one thing, and it's really overfitting. It's doing more than you should do. A statistical model in those kinds of situations for these wild or random functions is typically better, especially if it's clear that part of the data that you're coming at is from some real-life experiment where there's some noise, perhaps. All right, let's get into example 1. This is slide 1 for example 1. Our goal is to find a polynomial, p of x, of degree less than or equal to 4. Now, it's within the realm of possibility when you got 5 data points like this that the degree could be less than 4, though that's not likely, okay? That would be a very rare thing for that to happen. In all likelihood, it's going to be degree 4, and in fact, I've made it so it will be degree 4. It interpolates these 5 data points that you see here. Notice the subscript on these data points starts with a 0. That's going to be standard for us to start at 0. And the last point you can see is x4, y4. There are 5 data points. Keep that kind of thing in mind. The first data point is really sometimes called the 0th data point. These are the points that we want to go through exactly. Some terminology. The x's are called the nodes, and I will refer to those nodes quite often. In this case, they are -2, 1, 2, 4, and 5. Here's the first key idea. Try to write p of x as a linear combination, as in linear algebra, of what are called Lagrange basis polynomials, basis as in linear algebra as well. These Lagrange basis polynomials each have fourth degree. And here is the form of the polynomial. The weights are 36, 3, 8, 114, and 323. Those are the coefficients of the linear combination. You see a bunch of functions labeled with the letter L with some subscripts. The 4 in each subscript represents the fact that each of these is fourth degree. It's not absolutely necessary for me to include those things if that's understood. The second number, the 0, the 1, the 2, the 3, and the 4, represent the node at which each of these polynomials is equal to 1. It turns out that these polynomials are also equal to 0 at the other nodes. In a formula, you could say this: L sub 4 comma I at xj, where xj is a node, either x0, x1, x2, x3, or x4, is equal to 1 if I equals j, and is equal to 0 if I does not equal to j. In particular, for example, if I is 3, and we're looking at L4, 3 of x, you can see that this polynomial here, this fourth degree graph, is 0 at x0, which is -2, x1, which is 1, x2, which is 2, and x4, which is 5, and it equals 1 at x3. That's where I equals j. They're both equal to 3 in this case. Moving on to key ID number 2, these fourth degree polynomials that satisfy this property can be written quickly. Now when I say quickly, I don't mean literally you can write them down super quickly. What I mean is that there's a clear pattern to how they are written down. However, they do take a while to write down, but they're pretty easily programmable. The first one, L40 of x, would look like this. It's a fraction where the numerator is x minus 1 times x minus 2 times x minus 4 times x minus 5. And the denominator is -2 minus 1 times -2 minus 2 times -2 minus 4 times -2 minus 5. Does this really work? Sure. Notice that when you plug in the 4 nodes x1, x2, x3, and x4, which are 1, 2, 4, and 5, you get 0. Moreover, notice that when you plug in the first node, the 0th node, x0, which is -2, the top and the bottom are the same thing. They cancel to give you 1. This does work. And then you just repeat this trick for the other nodes. L41 of x is this. Notice this is going to be 0 at x0, which is -2, x2, which is 2, x3, which is 4, and x4, which is 5. And it equals 1 at x1, which is 1. Probably we should be making drawings of these things to try to help you remember that. When you plug in -2, 2, 4, or 5, you get 0. When you plug in x equals 1, you can see everything divides out to give you 1. Again, continue the pattern. L42 of x has a numerator that is 0 at -2, 1, 4, and 5. The 0th, 1st, 3rd, and 4th nodes, not the 2nd. At the 2nd node, x2 equals 2, it equals 1. You plug in x equals 2, and everything divides out to give you 1. Same kind of thing for L43 of x, same kind of thing for L44 of x. These are our quote-unquote quickly written down Lagrange basis polynomials. Now again, you form the linear combination of these to get p of x, and here's how it would look in unsimplified form. I do want to simplify this. I'm pretty sure there are no mistakes because I tried double checking everything, but it's conceivable there's a mistake somewhere, some sort of typo. I know the final answer is right. This would be a pain to simplify completely by hand, but not impossible certainly to do within maybe 5 minutes or so. Here's how the simplification goes. For example, -3 times -4, where'd my cursor go here? Oops. I don't know why it's not showing up for me. -3 times -4 times -6 times -7 is positive 504. And so in the first term you get 36 divided by 504. Keep going with the other ones. And then all these fractions can be reduced, like that. And then everything can be expanded. This would take probably more than 5 minutes, I guess, to expand all this. So I misspoke. Probably would take more like 10 or 15 minutes to expand all this, combine the like terms. And amazingly, for this example that I specially picked, it simplifies very nicely to this polynomial, x to the 4th minus 3x cubed plus 2x squared plus 5x minus 2. Here's the graph. You can see it's going through all 5 data points. For those 5 nodes, x0 equals -2, x1 equals 1, x2 equals 2, x3 equals 4, and x4 equals 5. And we have the corresponding outputs 36, 3, 8, 114, and 323. But I am only graphing the interpolating polynomial. I don't know the underlying function. There is a theorem that gives the error in the approximation if we do know the underlying function. Let me describe the theorem in this context. I'm not going to describe it in general here. For my students, it's in the book in general. Let AB be any closed interval containing the 5 nodes. Okay, most typically you probably imagine A to be the left endpoint, -2, the 0th node, and B to be the right endpoint, the last node, which is 5. But it could be bigger. The theorem is still true over a bigger interval. If we suppose f is the underlying function we are trying to approximate by fitting its values exactly at these nodes, and this is again how it differs from a statistical model. Here we're trying to fit the data points exactly, whereas in a statistical model we're trying to fit the pattern. If f has at least 5 continuous derivatives, this is part of the hypotheses of the theorem. Okay, 5 derivatives that are all continuous functions is what that means. 5 times continuously differentiable is the official way to phrase it. And written in this funny notation here, f is an element of the set C5 of AB means exactly that f has 5 continuous derivatives on the interval. Then for each fixed number x between a and b, there exists a number xi of x. That funny looking squiggle thing is a Greek letter xi. It's my favorite Greek letter. It's so beautiful. Xi of x between the smallest node and the largest node, between, in this case, -2 and 5, so that this equation is true. F of x, the underlying function we're trying to approximate with p of x, is equal to p of x plus some error term. Okay, some remainder it's sometimes called, but I think the word error term is better. What do you see here with the error term? You see an f5. Does that mean f5th power? No, it doesn't. It means 5th derivative. I could put 5 primes there, but you know, what if you had to put 50 primes? Then you don't want to put primes there in general. Or what if it's a general n derivative, n primes, meaning it's the nth derivative. This is standard notation, in this case for the 5th derivative of the underlying function, evaluated at this number xi of x. When you think about this formula, initially think about x as fixed. So xi of x is some fixed number as well. We're plugging in some fixed number into the 5th derivative of f, dividing by 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120, times this product, x plus 2 times x minus 1 times x minus 2 times x minus 4 times x minus 5. You may have seen something like this before in the context of something called Taylor's theorem. This is a generalization of Taylor's theorem. In other words, if I solve this equation for the error by subtracting p of x from both sides, and I call it, say, error of x, that error as a function of x can be written in this way, that you see with the 5th derivative of f at xi of x divided by 5 factorial times the product of those linear terms in x. Again, this is not so helpful in this example because we don't know f. It's still true, but we just don't know what f is. Now, if f is a really wild function, the 5th derivative could be some huge quantity, okay, and the product of those linear factors could be something huge. So the error doesn't guarantee that the error is really small in the usual sense of the word, like less than 0.1 or 0.01 or something. The error could be very large in theory. That's what I emphasize here. Even if we did know f, the error could be very large at certain values of x. It's not large at the nodes, right? There we get exact equality. Let's go on to example 2 now. So now we're going to assume we know the underlying function. It's going to be the sine function. Let's do it over the interval from 0 to pi over 2. And let's use as nodes, you know, we could use any number of nodes that we want, but let's go ahead and use the nodes that are have outputs that are often memorized. 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay, and these are not evenly spaced. The nodes don't have to be evenly spaced. That's a feature of this theory is that the nodes don't have to be evenly spaced, and these are not. What are the outputs? You should have those memorized. F of 0 is 0, f of pi over 6 is 1/2, f of pi over 4 is square root of 2 over 2, f of pi over 3 is square root of 3 over 2, f of pi over 2 is exactly 1. The input is assumed to be in radians, as it always is when you are applying calculus to trig functions. So don't think about degrees here. And we have approximate values for those things. So now we can go ahead and apply the exact same key ideas, those two key ideas, to write, in this case, again, a fourth degree polynomial because I have 5 nodes, as a linear combination of the Lagrange basis functions. And the second key idea is that the Lagrange basis functions are 1 at certain nodes and 0 at all the others. However, the calculations, as you might imagine here, are going to be much messier. Symbolically, it's going to be somewhat similar. Here would be L4, comma 0 of x. Notice this is 0 at pi over 6, pi over 4, pi over 3, and pi over 2, and equal to 1 at the 0th node, which is the number 0. Here would be L4, 1 of x. This is 0 at 0, pi over 4, pi over 3, and pi over 2. It's equal to 1 at pi over 6. This one's equal to 1 at pi over 4, and 0 at the other nodes. This one's equal to 1 at pi over 3, and 0 at the other nodes. And this one's equal to 1 at pi over 2, and 0 at the other nodes. So these would be the actual Lagrange basis polynomials. And now we form a linear combination of these where the coefficients, again, the weights in front of these things, are the outputs of the sine function at these nodes. These exact values, 0, 1/2, square root of 2 over 2, and square root of 3 over 2, and 1, which we can then approximate. Suffice it to say, most people don't want to attempt to simplify this without technology. We will go ahead and use technology. We'll use Mathematica in just a minute here. Here's what the approximate answer is. This function right here. Okay, and it's not as nice as that previous example. We have these decimals that you see here. Here is what the graph looks like. F of x is in blue. That is the exact sine function. P of x is in red. That's this fourth degree polynomial. You can't tell the difference between them. They look exactly the same, even though they're not exactly the same. Hope you agree that this is pretty amazing. The error is really close to 0. How close to 0? The error theorem can tell us. What about the error for this example? Certainly, the sine function is infinitely continuously differentiable. It's got continuous derivatives of all orders, and you know what they are, right? You can figure them out. In particular, we can say f is in C5 of a to b, where a is any number less than b. It's got a continuous fifth derivative, and we've got these 5 nodes. That's how we would want to apply the theorem. And in particular, the fifth derivative of f is the cosine function. And so, in absolute value, if I plug in any c of x for any x, I can say this is less than or equal to 1, because we know for real inputs, the cosine and sine functions, for example, are always less than or equal to 1 in absolute value. They're always between -1 and +1. That allows me to get a little bit more specific here with the error term. For any fixed x, the error of x in absolute value, often called the absolute error, is bounded above, it's less than or equal to 1 divided by 5 factorial. The 1 comes from the previous line. I'm just replacing that fifth derivative at c of x in absolute value by 1, times the product of the linear factors x, x minus pi over 6, x minus pi over 4, x minus pi over 3, and x minus pi over 2. We can get a little bit more specific, emphasizing that x itself is between 0 and pi over 2. We could say that all those factors in that product in absolute value are less than or equal to pi over 2. So I could say the absolute error is bounded above, in fact, by pi over 2 to the 5th power divided by 5 factorial, which is 120. And if you check that on your calculator, you'll see that's less than 0.0797. Actually, we can do a little bit better. We can realize that we can take each term in that factor individually. In absolute value, the x, since x is between 0 and pi over 2, will be bounded above by pi over 2 in absolute value. X minus pi over 6, if you draw a little picture and think about it, is bounded above by pi over 3 in absolute value. The distance between pi over 6 and pi over 2 is pi over 3. X minus pi over 4 is bounded above by pi over 4 in absolute value when x is between 0 and pi over 2. X minus pi over 3 is bounded above by pi over 3 in absolute value, and x minus pi over 2 is bounded above by pi over 2 in absolute value. This gives us a little bit better estimate. The error in absolute value is going to be less than or equal to 0.01771 as a guarantee from this theorem. What actually happens, though? the error is actually smaller. And you can see this from graphing. If you graph both, say, the error and the absolute error, you'll get this picture. The error itself is in blue. It can be positive or negative. Error is always actual minus approximate, f of x minus p of x in this case. So the error is positive when p of x is too small. F of x minus p of x is positive. And the error is negative when p of x is too big. F of x minus p of x is negative in that case. Taking the absolute value of that gives you the red graph. And you can see in absolute value, this is always less than or equal to 0.0003, right? Like that. So it actually does better than the theorem, and that typically happens in general. But if we want guarantees, we want to use the theorem. Here's a question that I could ask my students on a homework or a test question. And if you're watching this video and you're not my student, you may be asked a question like this as well. Based on the error theorem for this example, how many nodes would we need to guarantee from the theorem that the absolute error is less than or equal to 10 to the negative 6, 0.000001, over the same interval here from 0 to pi over 2. We can go back to the theorem and, well, we could go ahead and replace all those factors in the, the x minus the different nodes with pi over 2. We're not saying what the nodes are, so probably you should just play it safe and use a pi over 2 in each case. Raised to the n plus 1 power, that's the way the theorem phrases it, divided by n plus 1 factorial. We want that to be less than or equal to 0.000000001, which is 10 to the negative 6. Solve for a minimal n using trial and error. There's not really a way you can solve for n very easily here besides just using trial and error. You should check this on your calculator. If you do use trial and error, the minimal value of n as a whole number that makes this inequality true is n equals 11. And therefore, 12 nodes would guarantee that our error is less than or equal to 10 to the negative 6. Graphically, we might be able to get away with fewer nodes, however. Okay, that is possible. Before I go to our words of warning to end the lecture, and also to reading from the Bible to give you some encouragement, I do want to show you some Mathematica things. This is going to be especially relevant for my students, but even if you're not my student and even if you don't have Mathematica, you might be interested in seeing this. How did I generate my examples, and what can Mathematica do to save you some time, for example? This first bit of code here is just defining my polynomial. Actually, I didn't have an underlying function for the first example. I just used the polynomial essentially to interpolate itself. I wanted to know its values at the nodes negative 2, 1, 2, 4, and 5 here, and this input gives me output telling me what those the second coordinates of those nodes were: 36, 3, 8, 114, and 323. Those were the weights or coefficients of a linear combination in example 1. I did some other calculations in Mathematica to compute the coefficients, and expand will actually simplify the polynomial, and there's the simplified version. You can see it equals p of x. Here is a way I made the graph of L43 of x with this code here. So you can see how I made that graph and made extra kinds of things in it to label the points. This is the graph of p of x itself right there, including labeling the graph itself. And this code down here, underneath that graph, is especially interesting. This code, well, first of all, creates the data that I want to interpolate, the points. And this function, interpolating polynomial, actually does the Lagrange interpolation for me. Although if I don't do the / expand at the end, I don't see it in a simplified form, and it's kind of a weird form that it puts it in. But doing the / expand will give me a simplified form. I think I could do also / simplify. And by the way, that's called a postfix operation. I can also do the expand at the beginning if I like as well. There is p of x, it's the same thing. Here's some code for example 2, the sine function. And I went ahead and typed in all the Lagrange basis polynomials. Copying and pasting and making corrections helped save some time. And there we see p of x in expanded form based on the linear combination right there. I can use interpolating polynomial again to confirm the answer right there. Here's code that makes a graph of the sine function and its interpolating polynomial over the interval from 0 to pi over 2. The code that I got here left over, well, let's see. Let's do this one next. This one shows you a graph of the error and the absolute error. This one is a way to experiment to find a minimal value of n that makes the error less than 10 to the negative 6. And it's when n equals 11, yep, that we first get below 10 to the negative 6. And so n plus 1 is 12, and so you'd want 12 nodes. This code here I'm going to save for after I talk about the warnings, as well as a statistical example down here. I've got some more code. Forgot to mention this at the beginning. I will be sharing these files, by the way, not just with my students, but with everybody in the world who happens to watch this on a Google Drive. I'll put the links in the description below, and I'm sure before I process this video, I'll put a note at the beginning of the video about that. Let's talk about the words of warning. This is really important, okay? Words of warning when using this method and interpolation in general. In spite of the truth of the error theorem, the interpolating function in all likelihood will do a bad job at extrapolation. That's the first word of warning. Here's what happens in extrapolation, for example. Again, we were focused on interpolation in the interval from 0 to pi over 2 being about 1.57. You can see the 5 points there, the data points, and the red graph does a real good job between 0 and pi over 2. It even does a decent job, you might say, between about -1 and close to 3. Once you get outside that window, it's doing a bad job, okay? And yes, here's some Mathematica code showing that. This code shows the graph I just made like that. This is just the data there. I guess I don't really need that. Let's go to the second word of warning. Word of warning, slide 2. Again, a wild function, or it's got some randomness involved, maybe because of noise, might be overfit if we use polynomial interpolation. And this overfitting can even mean the interpolation could be bad. Here's a graph. There's a high degree polynomial for these data. I think I've got maybe around 20 data points here or so. If that's the case, then this would be a 19th degree polynomial trying to fit these data points exactly. You might say if there truly is a deterministic underlying function with no randomness involved, this seems to maybe be doing a good job in the middle. But when you get near the extremes here, and we're still interpolating, we're not extrapolating in here and over here, it's probably doing a bad job. It would seem more likely that you'd want to connect this a little bit more smoothly in here and over here like that. But the high degree polynomial is doing a bad job near the extremes. Certainly for extrapolation, it's doing a terrible job, most likely. And even for interpolation near the ends, it's doing a bad job. Here would be a better model to use, a statistical model, a low degree statistical model, using something called least squares regression, which I talk about in my other lectures on applied stats. It's usually better. Here, it's the same data as this picture here, but now we're fitting it with a straight line, a linear trend to the data. This low degree statistical model fits the trend. We're not, it's not going through any of the points probably exactly. Probably misses all of them. Some points are pretty close, but it probably misses all of them. More importantly, though, it's fitting the trend with some scatter, some residuals, you might say, above and below this regression line that's found with something called the method of least squares. That's the last slide in the PowerPoint. Let's go back to the Mathematica, and I'll show you how I made some things here. And then I will be reading from the Bible. This is the statistical example, if you're interested in this. So this makes some data where I purposely made the x coordinates deterministic. I could have made those random too. And I made the y coordinates 10n plus a random real number between -30 and 30, according to what's called a uniform distribution. Don't worry about that. That's the data, although if I re-enter this, I'll get different data. So did I just re-enter it? I don't remember. Maybe I did. I guess I did. Okay, so here I'm going to get different data than what I showed you to start with here. And I'll get a different interpolating polynomial. This is not the same example as before. But, again, it's not doing a great job near the ends. Fit is a command in Mathematica that will give you a linear regression model or even a quadratic regression model or cubic and that kind of thing. that doesn't go through any data points probably exactly, but follows the trend, okay? So, and again, this is a different data set than I had in the PowerPoint. Let me end, again, by reading from the Bible. Bethel University is a Christian liberal arts school, and I like to give my students all the encouragement that I can. If you're a Christian, I hope you take heart in the midst of the coronavirus from this. I'm going to read from Philippians 4, which is one of my favorite chapters. We'll start in verse 4 here, right there. Rejoice in the Lord always. Again, I say rejoice, okay? And it says always, not just sometimes. Sorry about that. It's not really, doesn't focus very well here, it seems. Always, not just sometimes, always, even in the midst of trials. And everybody goes through trials in their life, okay? If nothing else, the trial of dying, or the trial of losing a loved one to death is a trial, okay? And we all go through trials in school, in relationships, in jobs. That's the nature of life. But always rejoice in the Lord. Let your reasonableness be known to everyone. Up here now. The Lord is at hand. Do not be anxious about anything. Do not be anxious about anything. But in everything, by prayer and supplication, which is just, making requests of God, with thanksgiving, let your requests be made known to God, and the peace of God, which surpasses all understanding, will guard your hearts and minds in Christ Jesus. I pray that God would give you all health, peace, and the ability to keep working hard during this difficult time. Thanks for watching.